Working as part of a NASA-wide team, engineers from the Jet Propulsion Laboratory in Pasadena, California, have used software called Disruption Tolerant Networking, or DTN, to transmit dozens of space images to and from NASA's Epoxy spacecraft, located more than 20 million miles from Earth. To develop this new technology, NASA partnered about 10 years ago with Vint Cerf, a vice president at Google and co-inventor of the TCP/IP protocol used in the terrestrial internet.
In simple terms, it's like creating an internet in space that's like the internet terrestrially, but it has some different characteristics. Things are a lot farther apart in space. The distances between the planets are literally astronomical. And so the delays at the speed of light are very high compared to what they are on the ground. So the methods that we use for the terrestrial internet don't quite work when we're going at interplanetary distances, and we've concluded after quite a bit of work that we needed to design a new set of communication protocols.
DTN does not assume a continuous end-to-end connection. In its design, if a destination path can't be found, the data packets are not discarded. Instead, each network node keeps custody of the information as long as necessary, until it can safely communicate with another node. This store and forward method enables reliable delivery of information to the end user while tolerating disruptions in communication.
If you're doing space communications and you have something sitting on the surface of a planet and the planet's rotating, you can't talk to it until it comes back around again. And some satellites may behave the same way. You may not be able to see them to talk to them. So the communication in this deep space network becomes disrupted, and similar things happen terrestrially under some conditions. So the delay-tolerant networking is designed around the idea that things are not always connected, that you should not be expecting a response to come back right away. In fact, you're not even sure when it will come back. So you build your system to be very, very tolerant of an uncertain amount of delay and frequent disruption of communication.
Engineers began the month-long series of DTN demonstrations in October, using the Epoxy spacecraft as a simulated Mars relay orbiter. The DTN software ran continuously on board the spacecraft for 30 days, and data was transmitted using NASA's Deep Space Network twice per week over this period.
So what we're simulating here this morning is a probe on, say, a rover on Phobos. We just picked a name, a rover on Phobos, sending data to a lander on Mars via several hops of relays.
All right, all stations, we have confirmation. The experiment data has been received. Flight copy. Congratulations.
This experiment was the first in a series of planned demonstrations to qualify the technology for use on a variety of upcoming missions. In the next few years, interplanetary networking could enable new types of exploration. Complex missions involving multiple landed, mobile, and orbiting spacecraft will be far easier to support through the use of the DTN.
Well, the general public probably doesn't pay a lot of attention to the details of infrastructure. They don't think about the Deep Space Network or about the protocols of the internet. They just use it. And so I think if they could be excited about this at all, it will be because we will be enabling more scientific information to come back from much more complex experiments, learning more and more about the solar system and its origins and its ultimate destination. Maybe a lot more about whether life could exist in the solar system or whether it ever has existed. And even using spacecraft to look further and further out into the universe to understand more about its origins. So they should be excited about this because it's enabling our scientists to do more than they ever did before with space-based exploration.